in terms of conflict between hardware and software, you have hardware on the left with some very unfortunate components. If you want to make your own hardware, what I mean by this is, of course, make your own ASIC, make your own chip. ASIC is an application-specific integrated circuit here. So you want to make your own little black chip with legs coming off and the thing that you solder into a PCB. You may need up to $1 billion in order to really build a competitive one, really make one that can take on the leaders of computing today. Most of that money is actually in the software to drive that chip. But it doesn't matter. Whatever it is, you need somewhere around $1 billion budget to really take on the top players in this world. Companies like Amazon have that type of budget, and they've started recently to take on the main companies, NVIDIA, Intel. IBM has slightly dropped out of the race because the billion started to be too expensive for them. And it takes years. So the order of magnitude is years, but you get the fastest implementation possible. Really, really fast. Over there on the right, you have software. Now, software, you can write a few thousand US dollars. You can get you some kind of software written, use some libraries, maybe use Python to make things really easy and quick. And you can write stuff in a matter of days. You can sit down 2-3 days later, you've created a new AI. You've created something that makes the world a better place in some way, computationally. And it can be very easy, but it may take a very long time to execute. So in between both of these things, you have a conflict between hardware and software. People sit there and say, should I make hardware out of my problem, or should I do the software? The people who have $1 billion, they say, tell me what it is that you want to put into my chip, and I'm going to make a chip out of this. The people who write software say, I don't want to tell you what it is that you should put into your chip, because we just want to write the software and want to change it every day, because our job is to write the software. And the moment we give the software to you, we can't get our salary anymore. There's nothing to do because the software is locked in. Now we have to stop developing the software because you have locked it into the ASIC. So we won't want to give you the software to put onto an ASIC. We want to keep it in software. And so there's a natural conflict between computer science and electrical engineering, between people who make the ASICs, the chips, and between people who want to keep everything in software, and they want to keep changing everything on a daily, minute-by-minute basis, because that's what they do. And between these two mega markets, each one of these hundreds of billions of dollars, you have a tiny, tiny little market, which is the flexible chips. And so there have been a group of people being squished between these two giants, trying to show that you can have a trade-off with a little bit of flexibility in hardware. You can offload your CPU computation. You can prototype your ASIC before you make your ASIC. You can build an FPGA. But it's an activity that is limited in time and space, because at some point it's swapping either over to the left or to the right. So you have a metastable state. If I want to explain this to deep electrical engineers, there's a metastable state inside of FPGAs and with FPGA technology, which ruins the game for both the hardware people and the software people. But it provides a nice little middle ground. And if you have an actual challenge, an actual problem in computing, it many times can be the winning solution, where you can do something in a matter of months, and it runs almost as fast as the custom hardware. And what I've been working on over the years is making these months go down to weeks or to days, and provide a trade-off, a benefit between keeping everything in software or moving everything into the hardware.